Hello students, in this video tutorial we will see the last type of LR parser. It is also called as look ahead LR parser and short form is LALR. So before starting the LALR you must understand or you must know the meaning of items, what are the LR0 items, what is SLR parser, what is CLR parser, and in what way the parsing tables are created in the respective type of a parser. So the main difference between all the types of parser is nothing but in what way the parsing table is constructed. So we will start with the LALR parser. So in the LALR parser, the L and A stands for look ahead. That means we are having a look ahead symbol in the given grammar. So now based on that we can say that the LALR parser is an extension of CLR parser. That means the steps that you have performed to construct the CLR parsing table, we have to repeat the same steps in the creation of LALR parser. So the basic idea in the LALR parser is that it will generate the less number of states as compared to CLR parser. If you have observed in the last video, I have explained CLR parser where the number of states are more, just because though the grammar is similar, grammar is same or the production rule is same, but the difference lies in the right hand side of comma, that is in the look ahead symbol, and because of the look ahead symbol we are treating those states as the different states. Because of that the number of states got increased, but in the LALR parser it is not happening. So we are reducing the number of states. So the SLR and LALR, these two types of parser are having less number of states as compared to CLR, and the count is almost equal to each other. But the LALR parser is more powerful just because it is generating more number of grammars than the SLR parser. So we can say that the LALR parser is most widely used or most oftenly used type of a grammar. The YAK, that is the parsing tool, it creates the LALR parser or uses the LALR parser for the given grammar. As I said earlier, the LALR parser will also begin with the collection of LR1 items. That means the same steps we have to repeat as similar to the CLR parser. So if you observe this diagram, we will first of all create the canonical LR parser, that is CLR parser will be created. Then after that whatever number of states we have created, it will be shrinked or it will be reduced, and we are going to create the LALR type of parser. So this is the basic idea of creating the LALR parsing table. So start with the construction of CLR type of parsing table and just have the reduction on the number of states, and you will be getting the LALR parser. We will be considering the same example that we had discussed in the CLR parser. So because of the shrinking of state, what actually happens, we are creating the LALR parser, but this LALR parser is having some sort of conflict in it. That means the shrink process may introduce reduce conflict in the resulting LALR parser, but we do not have any shift reduce conflict. Meaning is that we are actually combining some states. So while combining those states, there may be a chance that reduce to reduce conflict will occur. Now what idea that LALR parser is giving us? LALR parser is allowing us to merge the two states into a single state. That means we have to find out the two states having same cores. What we can say, the core is nothing but the part which is coming after the arrow symbol in a given production. So before look ahead, whatever we have that can be called as core. So core of two production has to be same, or core of two states has to be same. Then we are able to merge both these different states into a single state. So in this way we can reduce or we can shrink the number of states. So hereafter on the next slides I am discussing the example similar to the CLR parser. So you can refer to the previous video where you will be getting some idea about the CLR parser along with the example based on it. At the end I will explain you how this CLR parsing table is converted into LALR parsing table. So hereafter we are having the similar example as that of CLR. So this was the example we discussed in the CLR parser video, where the given grammar is like this, and we created in the first step augmented grammar. Then we started finding the LR1 items. This is the state I0 we got. From I0 we obtain the different transitions, that is go to operation, and we found the closure. So I0 to I1 we obtained. After that I2, I3, I4, I5, I6, I7, I8 and I9. So this is what we have already seen, that get a state. On that state what go to operation is possible, that is transition is possible, and at last perform the closure, so get the productions collected in a state. So up to I9 state we have obtained LR1 items, and this was the DFA created for the same. So all states are listed here and their corresponding transition, and we have performed the closure operation. So the state and their production is combined here. Then we started applying the shift operation. So from state 1, state 0 to state 1, 2, 3, 4, 5, 6, 7, 8, 9. So up to 0 to 9 we obtained possible shift operations. Then we saw about the reduce operation. Then in what way we collected the candidate states that are considered as a final state, that is dot at the end. Then these states are mapped with the production rule, and we created the reduce operation for them. So state 4 reduced to R3, then state 5 is reduced to R1, then state 7 is reduced to R3, then state 8 is reduced to R2, and state 9 is reduced to again R2. So in this way we applied the reduce operation, and at last we created this kind of final parsing table for the CLR. So here you can observe the number of states are more, okay, in the CLR, and these states are having different shift and reduce operation corresponding to them. Now while creating the LALR parsing table, what we have to consider, we need to check the states that are having similar type of production rule, but they are differing with respect to their look ahead symbol. So I have collected some of these states from the given grammar. So I3 and I6, you can observe the production created by I3 and I6 is similar, only change lies in their look ahead symbol. Similarly, two such state, that is I4 and I7, you can observe they are having the similar production but look ahead are different. Similarly in I8 and I9, the production is similar but look ahead are different. So just make a pair of such type of states together, and we will create a state kind of I36, I47 and I89, so that the number of states will be lesser as compared to CLR parser. So here I3 and I6 combinedly we form I36, whereas the production will remain same, only change will be look ahead is added together, that is C or D or dollar. In this way we will create the I36 state. So you need to mention this I36 state, okay, where the production is written as it is, only the look ahead are added together. Similarly I4 and I7 combinedly form I47, the production is similar and look ahead are added together. Similarly I8 and I9 forms I89, production is written and look ahead are added together. So we will update I36, I47 and I89 into the CLR table. So this 3 becomes 36, this 4 becomes 47, and this 8 becomes 89. In this way we will update our existing CLR table. So this is the way we update the states that are combined together. This is called as shrinking of the state. So I36, I47 and I89 will become the part of this state column. Now just look into this table. We have I36, I47, I89 together. This is the CLR table. We need to make update into the CLR table. So what we will do, we will combine 3 and 6 together. So 3 and 6 combinedly forms 36. 3 is having shift operation on C and D. 6 is having shift operation on 6 and 7. So we will have combination of this shift operation as shift 36. So shift 36 is possible since we have introduced new state, that is I47. So the shift of 3, that is S4, and shift of 6, that is S7, can be combined and form S4 plus S7 can form S47. So shift to 47 is possible. So there is no shift conflict. Now next is, let us consider state 4 and state 7. So 4 and 7 are combined together. So 4 and 7, that is R3 with 4 on C. R3 is when 4 on D. 7 is not having any operation over C and D symbol. 7 is having only operation R3 over the dollar symbol. So 4 doesn't have anything on the dollar symbol. So this can be combined together. So there will not be any reduced conflict while combining 4 and 7 state. And last one is 8 and 9. So 8 is having R2 on C and D, and 9 is having R2 on dollar. So both are combined together, so no reduced conflict is there. So in this way we have combined together. So just observe, in the state 3 and 6 we perform the action part with the combination of shift operation. Now in 3 and 6, if you observe, 3 on C gives rise to 8, whereas 6 on C gives rise to 9. So we will combine this. 3 6 on C goes to 8 9. So 3 6 on C goes to 8 9, and we have state 8 9 possible. So this also also doesn't produce any conflict. So in this way this type of LALR parsing table is prepared. So just compare the CLR parsing table and LALR parsing table. The number of states are reduced. So we have around 7 states here, and we have total 10 states here. So 3 states are shrinked, that is reduced, and we form the combination of those states. Also we combine the shift operations together. So in this way LALR parser table is prepared. So now we'll look into the LALR example. The input string given to you is ADD. So the steps are similar to the previous types of parsing examples, where you prepare a stack. Top of stack will be the 0, that is first state. Then prepare the input buffer. So put this string into the input buffer, that is ADD, and end with the dollar. Now take your parsing table, and with parsing table we will see which input symbol get reduced to which production based on the parsing table, and just number your production rows, that is 1 2 3 4 up to the last production. So in this way we write the given data, and we start preparing the required data structures to solve the example. So before going to the example, just look at the parsing table one more time. What we have done, we have combined the states together. It is 3 and 6 are producing same type of production, only difference in the look ahead. So both are combined. 4 and 7 are combined, and 8 and 9 are combined. So here the state number is reduced. So 3 6 4 7 and 8 9 it is there. Now this 3 6 4 7 8 9 will also should be reflected in the action part. So in the action part, here you have S3, so it will become S36. Here it was S4, so it becomes S47. Here it is S6, so it becomes S36. Now instead of S7 you will have S47. Then for the 3 6 you will have S3, instead of 3 it will be S36. Here it will be S47. Next, this is already covered. Yes, these are the changes that we need to make for the shift operation. So no single state is there. The combination of two states are there, and that number is used. Now state 3 is not there, state 6 is not there. Instead it is called as state 36. So the same numbering we have to use while mentioning the shift operation. So shift operations are like denoted in a same way. Now we will see the example where input string will be ADD. So in the next part we will see how we can solve the example. You have to see whether the given input string, that is CDD, it is accepted by the parsing table or not. Okay. So now we will be starting with the example part. So here you can observe the parsing table I have taken, which was created previously. Then the given input grammar is like this. The grammar is splitted, so C tends to CC and C tends to D. Both are different production rules, and just give numbering to them, that is 1 2 3. The input is given as ADD, so we have to check whether this type of input is passed by the parsing table LALR parser or not. That we have to check. So first step is simple: get the input string into the input buffer. So it will be A, D, D, and at the end we have to write the dollar. And the very first step, very first element of stack will be the state number 0. So always top of stack is nothing but the state number. You have to remember this. So now look from 0 to the given input, that is A. So instead of A, what we can use? Let us use C basically here. So we can use C for this. So it will be CDD, and I will make change here CDD. Okay. So just because C is the symbol present, so now see the string 0 on C. So 0 on C possible? Yes, it is possible. It is shift operation. So it is shift operation. Shift what? Shift 36 operation. So we will shift this symbol, that is a 0 C, and the state number, that is 36. It shifted onto the stack. So input is processed. Move the input pointer. Now input will be D, D, and dollar. So now check 36 on D. What we have to see? 36, that is top of stack on D. So 36 on D, it is shift 47. So it will be shift 47. Fine. So we have to shift this 47. So it will be 0 C 36. The symbol is D, and what we have to shift, that is the number 47. So D is shifted. Now remaining input string is D and dollar. Now see from 47, that is top of stack, to D. So 47 on D, it is nothing but reduce. So reduce with the third production. What is third production? It is C tends to D. So what we have to do? We have to reduce up to the handle D. This is nothing but the handle. So this is the checkpoint. You have to pop out the element from stack till you get the D. Or just like previous videos, the simple rule is get the number of symbols on the right hand side, that is one symbol. So for one symbol remove 2 stack entries. So remove 2 stack entries and insert this into the stack, that is push C onto the stack. So what we will do, we will remove the entries, that is 47 and D will be removed, and instead of that C will be inserted. So it will be 0 C 36 as it is, and C will be inserted. Fine. So we have reduced this D with a C by using production number 3, that is R3. Now what we have to do, we have to find out the go to operation, that is go to which state. So go to is calculated by, see the previous top, that is 36 on C. So 36 on C is nothing but the 36 on C. Sorry, this is not small c, this is nothing, this is terminal, this is non-terminal C. So 36 on C is nothing but 89. So we have to push 89. Fine. What is the remaining string? D and dollar. So 89 on D. Just look at 89 on D. 89 on D is nothing but R2 operation. So again use the reduce operation. Reduce with the second production, that is C tends to C. So we got the handle, that is C. We got the handle, that is small c. So you have to remove the symbols till you get this terminal c. Or second method is that how many symbols are there on the right hand side? 2 symbols are there. So 2 into 2, that is 4 stack entries we have to remove. That means 89, this c, 36 and c we have to remove, and we will insert the left hand side, that is capital C. So this will be inserted. Fine. And all these 4 symbols are removed. Now the top of stack, that is go to operation, is calculated by, go to is calculated by, here go to was 89, here go to is calculated as 0 on C. So 0 on C is nothing but 2. So 2 will be the new top of stack. So go to 2. Next is C, 2 on the remaining string, that is D dollar. So 2 on D. So 2 on D is nothing but shift operation. So shift 47, this will be the operation. So 2 on D is shift operation. 2 0 C 2 D will be shifted and 47 will be shifted. So in this way we get D and 47 inside the stack. Now next is look from 47 to dollar. So 47 to dollar is nothing but R3. So reduce with the third production, reduce with C tends to D. So D is the handle. So we have to pop out the element up to D. So 2 symbols, or look how many symbols are there on right hand side? 1 symbol. So remove 2 stack entries. This will be removed. So 0 C and 2, and insert the left hand side. So C is inserted. Now compute the new go to, that is new top. So 2 on C. So 2 on C is nothing but 5. So this 5 will be the top of stack. Now from 5 look at the dollar. So 5 on dollar is nothing but R1. So again perform the reduce operation. So reduce to 1. 5 on dollar is R1. So reduce to 1. So S tends to CC. Both are non-terminal. So S tends to CC. So again 2 stack entries. So remove 2 symbols. So remove 4 stack entries. So we have to remove 1, 2, 3 and 4 and insert this S. So 0 and S will be the contents. Now what we have to do? We have to perform the go to operation. So go to is calculated as 0 on S. So 0 on S is nothing but 1. So go to 1. So new top of stack will be 1, and remaining input is dollar. So 1 on dollar. If you see 1 on dollar in the table, 1 on dollar is nothing but the accept. That means the string we have given as an input is accepted. So see, the input was C D D. First we have shifted C, then we shifted D, and now it got reduced, this D got reduced to C, so it becomes the C. Then in the next step we have this C and C together, it got reduced to C. Fine. Then this D is coming as it is, and this D got reduced to C. Now we have C and C combined together, and C and C is nothing but your S. So you started with the input string, you applied the reduce operation, and you get the starting symbol. So this is nothing but the bottom up parser. So in this way you have to solve the example. We started with the given table, given grammar, numbering to them the input string. The input string is CDD, not ADD, because a symbol is not present, that is why it is CDD. Just add this CDD into the input buffer, prepare the stack, and simply see the parsing table entries and perform shift or reduce operation. In this way this particular string CDD is accepted by the grammar.